Okay. Now the force of gravity is equal to the mass of the sun times the mass of the dust particle over our distance to the sun squared times the universal gravitational constant g. Now, that mass of the dust particle is just 4/3 pi times the radius of the dust particle cubed times the mass of the sun times the universal gravitational constant divided by the distance to the sun squared. Now, particles that go in a straight line go because their net force is 0. That means that the force of gravity and the force from the radiation pressure have to be equal to one another. So what we do is we set the force of gravity and the force of the radiation pressure equal to one another. That means the power of the sun times the radius of the dust particle squared divided by 4 times the speed of light times the distance from the sun squared equals 4/3 pi times the radius of the dust particle cubed. Oops, I forgot. We need to put in the density of the dust. Times the density of the dust times the mass of the sun times the universal gravitational constant over the distance to the sun squared. Now I want you to notice both of these forces fall off like the distance to the sun squared, which means that effect cancels out. Second important thing, the pressure force, the radiation force on the dust particles, only increases like their cross-sectional area, which goes like the size squared. But the mass increases like the volume, which goes like size cubed. So when I cancel out 2 of those powers of r, I'm left with just 1 power of r over here. Then I can easily solve for the radius at which these 2 forces are the same. That radius is going to equal the power of the sun times 3 from this 3 here divided by, I've got this 4 and this 4. That's going to be 16. The pi goes over there. C stays. Density goes over. Mass of the sun goes over. And the universal gravitational constant goes over. That will be the radius at which the force of the radiation pushing on the dust matches the force of gravity. The exact values for these can easily be looked up on Wikipedia or in many reference books. They're also in your text, and you can look them up there. I'm not going to do that right now, but it turns out that this is about 1.7 times 10 to the negative 7 meters. That is a tremendously small particle of dust, but it is bigger than you would expect for an individual gas particle. So very small particles of dust flow out in a straight line. Even smaller particles of dust would be pushed back beyond the straight line. They're pushed outward by the radiation pressure more than they're pulled in by gravitation. Slightly larger particles of dust come closer to following along the orbit of the comet. Really large chunks would just stay with the comet and hardly separate out at all. In fact, they may stay in the comet's orbit and become meteor showers later on, just as the comet evaporates. But the very small bits of dust follow in nearly straight lines, depending on their exact size, and form this curving dust tail that we see in pictures of the comets such as this one.